Welcome back to Fundamentals of AC Circuits. In this video, we're going to discuss band pass and band stop filters. So the objectives for this video are that you'll be able to design a series or parallel resonant band pass filter or a series or parallel resonant band stop filter using capacitors and inductors. And we're also going to learn how to illustrate the frequency response of a band pass or a band stop filter. So let's begin with a band pass filter. A bandpass filter allows a certain band of frequencies to pass through the filter while rejecting all other frequencies that are above or below the pass band. To create a band pass filter, we make a combination of a low pass and a high pass filter. So you can see here's our input voltage, which is fed into a low pass filter. The output of the low pass filter is fed to a high pass filter, and then the output from the high pass filter is what we're actually measuring. And that is what we use to construct a band pass filter. So the critical frequency of a low pass filter and the critical frequency of a high pass filter determine what your pass band is. So again, when we construct a band pass filter, we have a low pass filter in series with a high pass filter, and your two critical frequencies of each individual filter determine what we call the pass band. So if you look at the diagram here, the pass band is illustrated as the critical frequency from your high pass filter and the critical frequency of your low pass filter. So these frequencies that fall in between those two values construct your pass band. And if we look at a curve for the low pass filter, that would be the one in darker blue. The low pass filter is blocking your higher frequencies. If you look at the curve for your high pass filter, that's the curve in the lighter blue color. And your high pass curve is going to block your lower frequencies. And then there's a point where they overlap. And that point where they overlap is what's going to make up your pass band. And those are the frequencies that are allowed to pass. So anything within the pass band will pass. Any frequency outside of the pass band will be considered as a rejected signal. So the bandwidth of a band pass filter describes your pass band or the range of frequencies that are allowed to pass. And the bandwidth is defined as the difference between the critical frequency of your low pass filter and your high pass filter. So our definition for bandwidth is that it will represent the range of frequencies for which the current and therefore the output voltage is equal to or greater than 70.7% of its value at the resonant frequency. That's our definition of bandwidth. So we have that keyword resonant frequency. So today we're actually going to be using the concept of resonance to design our band pass and later our band stop filters. So when we talk about the bandwidth, that's going to represent our pass band, and a frequency will pass as long as the output is greater than or equal to 70.7% of the input value. For a typical bandpass filter, we have what's called a response curve. So when we talked about high pass and low pass filters, we discussed drawing a Bode plot. Rather than drawing a Bode plot for a bandpass filter, we're going to draw a response curve. And this is an example of a response curve. Notice that you'll have your Vmax, which is your maximum output voltage. Your Vmax is going to occur at what we call F0, or the center frequency. So I'll discuss how we calculate that in a minute, but the center frequency is going to lie directly in between the two critical frequencies that identify your pass band and therefore your bandwidth. The center frequency falls directly in the middle between these two frequencies. And at the center frequency, you'll have your maximum output voltage. At each of your two critical frequencies, you're going to have 70.7% of your maximum output voltage. That's what you will measure. Again, that's still called the minus 3 dB voltage level as well. So this is what a response curve looks like, and it very clearly shows what frequencies are allowed to pass through. Anything outside of your two critical frequencies, either higher or lower, is going to be considered a signal that is rejected, and you'll know that it's a signal that is rejected because the output voltage you're going to measure is going to be far lower than your maximum output. So we're going to start with learning how to create a series resonant band pass filter. Notice we have an inductor in series with a capacitor. And then we have a resistor. We're going to measure the output voltage across the resistor. So this is a series circuit where we're measuring the voltage across the resistor. So the output across R has a bandpass characteristic with a maximum output at the resonant frequency. Now the resonant frequency is called F0 when we're looking at a bandpass filter or a band stop filter, but it's the same resonant frequency that we've learned to calculate in previous videos. Another word for the resonant frequency when we're talking about bandpass filters is the center frequency. So those two terms are interchangeable when you're designing a series resonant bandpass filter. The center frequency is the same thing as the resonant frequency. And the center frequency is the point at which you're going to have your maximum output voltage. Now, why does that happen? If you remember our discussion about resonance, at the resonant frequency, the impedance of your inductor and the impedance of your capacitor are equal and opposite, meaning they will cancel each other out. So the resistor is the only element in your circuit. This effectively will look like a short. And so if we were to look at the voltage across R, it's going to be at its highest point when these two impedances cancel each other out. So the only impedance in the circuit is R. That means your input voltage is going to become the output voltage across R. When you're not at the resonant frequency, these two values, the two values for the impedances for the inductor and the capacitor, will no longer be equal and opposite. So you will have an impedance that's going to affect the output voltage of your circuit. So at the resonant frequency, we're going to get our maximum output voltage at that point. So this is how we build a series resonant bandpass filter. And for frequencies that are above or below the resonant frequency, the output voltage will drop off dramatically. So that's why we have this bell-shaped curve here. So when we get close to that center frequency, the signal will pass. And as we get further away from it, the signal will be rejected and the output voltage will decrease very rapidly. This is an example of a parallel resonant bandpass filter. Notice that the inductor and the capacitor are in parallel here. And we're going to measure the output voltage across that parallel combination. So the maximum output voltage here is achieved at the resonant frequency. We're going to have the maximum output voltage whenever the impedance of L and C are equal and opposite, and that occurs at the resonant frequency. Again, you'll have a response curve that looks similar to the one that I showed on the previous slide, where you'll see that as you go further away from the resonant frequency or the center frequency, the output voltage will drop off dramatically. So to calculate the center frequency, which is F0, or the resonant frequency, which is F sub R, for a series or a parallel resonant filter, we're going to use the formula shown below. So our center frequency is 1 divided by 2 pi times the square root of L times C. We're also going to use the quality factor as we determine the bandwidth of our filters. Just as a review, in a parallel resonant RLC circuit, the quality factor is determined by RW of the coil. Remember, that's the winding resistance of your inductor. In a series resonant RLC circuit, the quality factor is determined by both the resistance and RW. So these are a review of the formulas that we've discussed previously about determining the quality factor. We're going to use the quality factor to determine the bandwidth. So the bandwidth is going to be your center frequency divided by quality factor. The bandwidth is going to tell us how large or small the window is for the frequencies that are going to pass through the filter. The range of the frequencies will be determined by your critical frequencies and the center frequency, but the bandwidth tells you how large or small that window will be. The total impedance of a non-ideal parallel resonant circuit is as follows. This is again a review from our previous lecture on resonance. The impedance at resonance for a non-ideal parallel resonant circuit is RW times Q squared plus 1, where Q is the quality factor of the coil. Remember that at resonance, L and C appear open, and the source is only going to see that impedance of RW times the quantity Q squared plus 1. So now let's do some examples. A high-pass filter with a critical frequency of 2 kHz and a low-pass filter with a critical frequency of 2.5 kHz are used to construct a band-pass filter. Determine the bandwidth of the pass band and what frequencies are allowed to pass. So remember that the bandwidth is equal to your critical frequency of your low-pass filter minus the critical frequency of your high-pass filter. So we're going to design this filter in such a way that these two critical frequencies will provide the pass band. The pass band is going to be 2.5 kilohertz minus 2 kilohertz, which is 500 hertz. So our window is, we have a 500 hertz window of frequencies that will pass through. Now, what frequencies will actually pass? Anything between 2 kilohertz and 2.5 kilohertz will pass. That's your window of frequencies that will pass through this filter. Anything higher than that or lower than that will not pass. So now we have a series resonant band-pass filter. We're going to determine the center frequency, determine the bandwidth of the filter, determine the output voltage at the center frequency, and sketch the response curve. So let's start with the center frequency. 1 divided by 2 pi times the square root of L times C. There's our center frequency. So we know at that point we're going to get the maximum output voltage. And we know at that point that's the resonant frequency. At that point the impedance of these two components will cancel out. And the only impedance I'll have in the circuit is R along with RW. So now we're going to determine the bandwidth. First, we're going to find XL by doing 2 times pi times the center frequency times L. And then we're going to determine the quality factor. This is a series resonant band-pass filter. So our quality factor is XL divided by R plus RW. The quality factor is a ratio, so it does not have a unit. Then we're going to use the quality factor to determine the bandwidth. So I know the center frequency is 107.3 kilohertz, and the bandwidth is 17.5 kilohertz. The bandwidth represents how large the window is. The center frequency is my center point or my direct middle of the window of frequencies that will pass. So the output voltage at the center frequency. So remember that when we're at the center frequency, the circuit is at resonance. The impedance of the inductor and the capacitor are equal and opposite and will cancel each other out. That means that the only impedance you have in the circuit is the winding resistance and the resistor itself. So imagine that these two components have been replaced with a short, and the only other thing that we have in the circuit is the winding resistance. So if I were to set up a voltage divider to find the output voltage, I'd have 100 divided by 100 plus the winding resistance times 10 volts. So my output voltage is 9.09 volts. That represents my maximum output voltage that I'm going to get for this particular bandpass filter. If this were an ideal circuit and there were no winding resistance, I would get 100% of the input at the output. The winding resistance is what causes the output to be slightly less than the 10 volts that we started with. Now we're going to sketch the response curve for this particular filter. To do this, you're going to start by drawing an XY axis. Then we're going to add our center frequency. And then we're going to add our two critical frequencies, one to the left and one to the right. But how do we determine these? These two frequencies are based on where your center frequency lies and the width, the bandwidth. How wide is the window for the frequencies that can pass? So this is the middle of the bandwidth. And I know the entire bandwidth is 17.5 kilohertz. So to find my two critical frequencies, I'm basically going to take the center frequency and I'm going to do plus or minus the bandwidth divided by 2. Take the bandwidth and cut it in half. I know that I have to go forward by that amount and I have to go backward by that amount so that this entire window right here represents my bandwidth. So these are my two critical frequencies. Notice that they are exactly 17.5 kilohertz apart. Next, I'm going to label the maximum output voltage I can receive, and that's going to be the maximum voltage you will observe at the resonant frequency, which we previously calculated to be 9.09 volts. Next, I'm going to label what 70.7% of my maximum output voltage is. That's 6.43 volts. I'm going to draw a reference line at the center frequency, a reference line at my maximum output, and a reference line at 70.7% of my max. And there's my curve. A few things about the curve. The top of the curve, your maximum point, should touch your reference line for the maximum output voltage. Your line for 70.7% of your max should coincide with your two critical frequencies. Notice that this critical frequency reaches this point. This critical frequency reaches this point. Because at these two critical frequencies is where you're going to have 70.7% of your maximum output voltage. So from this point to this point, these are all the frequencies that are considered to be passing, and the voltage that you will measure at the output we can read from this graph. So if I were to input a frequency that's maybe right about here, I can use this graph to determine what output voltage I expect to measure from that particular filter. Frequencies that are outside of the pass band are considered frequencies that will be rejected. They do not pass through the filter. Now let's look at a parallel resonant band-pass filter. So if you look at the circuit given, the inductor has a winding resistance of 15 ohms. We're going to determine the center frequency, the bandwidth, the output at the center frequency when the input is 12 volts, and we're going to sketch a response curve. So beginning with the center frequency, we have 1 divided by 2 pi times the square root of LC. There's our center frequency. Next, we're going to use that center frequency to find XL. I'm using XL to then find the quality factor. This is a parallel resonant bandpass filter, so quality factor is XL divided by RW. And then I'm using the quality factor to find the bandwidth. So now I know the size of the window of the frequencies that will pass. Since this is a parallel resonant bandpass filter, we have to compute the impedance that's going to be observed at resonance using the formula RW times the quantity Q squared plus 1. Remember that at resonance, L and C appear open, and the source is only going to see ZR as the impedance at that particular branch. Now our output becomes a voltage divider, where we have ZR divided by ZR plus R times 12 volts. So our output at resonance is 11.997 volts. And now we're going to sketch the response curve. Here's my axis. There's my critical frequency. Again, I have to calculate, that's my center frequency, and now I have to calculate my two critical frequencies to the left and to the right. I'm going to do that by taking the bandwidth, cutting it in half, and then I'm going to take my center frequency and do plus or minus that value. So there's my two critical frequencies to the left and to the right. My maximum output voltage and 70.7% of my maximum output voltage. A few reference lines so that my curve can be nice and smooth. And there's my curve. Again, remember that your two critical frequencies should align with your 70.7% maximum. And your peak occurs at the voltage maximum. So there's my frequency response, or the response curve, for this bandpass filter. Now we're going to talk about band stop filters, which work in the exact opposite way of a bandpass filter. It allows all frequencies to pass except those that lie within a certain stop band. So where the pass band was before, we've replaced that with the idea of a stop band. Within the stop band, these are the frequencies that do not pass. Anything outside the stop band will pass. Notice that to create a band stop filter, a low pass filter and a high pass filter are now wired in parallel. For a band pass filter, they were wired in series. So we still have two critical frequencies and a center frequency. And we still have a low pass filter and a high pass filter that are used to make the band stop filter, but the orientation is a little bit different and the behavior is the reverse. So now anything outside of the stop band is allowed to pass through. Here's our response curve for a typical band stop filter. At our center frequency, we're going to have our minimum amount of voltage, the lowest amount of voltage you're going to get out. And as we get further and further away from the center frequency, the output voltage is going to increase until we get to a signal that is going to pass, where the output voltage is going to be very, very close, if not exactly equal to, your maximum output voltage. So for a resonant band stop filter, you can have a series formation on the left or a parallel formation on the right. So these are our series resonant filters that are band stop filters. So the same information that I've already given for a band-pass filter can be used to find the following for a band stop filter: bandwidth, the center or resonant frequency, upper and lower critical frequencies, your quality factor. All of the other information that's already been provided is exactly the same for a band stop filter. So we're going to use that information to do the next example. So a high-pass filter with a critical frequency of 2 kilohertz and a low-pass filter with a critical frequency of 2.5 kilohertz are used to construct a band stop filter, determine the bandwidth of the stop band, and what frequencies are allowed to pass. Well, our bandwidth is still determined by the same values, subtracting our critical frequency for the low filter and our critical frequency for the high-pass filter. So we have 2.5 kilohertz minus 2 kilohertz, 500 hertz. That's the window of the stop band. That's our bandwidth. But now, frequencies that are below 2 kilohertz and above 2.5 kilohertz will pass through. So let's look at a series resonant band stop filter. The inductor has a winding resistance of 2 ohms, and we're going to determine the center frequency, the bandwidth, the output voltage, and sketch the response curve. Starting with the center frequency, we have 1 divided by 2 pi times the square root of L times C. So we have a center frequency of about 5 kilohertz. To determine the bandwidth, I need to know XL. I'm going to determine XL based on the center frequency. And then determine the quality factor. Remember, this is a series resonant circuit, so use the correct formula for quality factor here and plug that in to find your bandwidth. So I have a bandwidth of 92.33 hertz. Next, I'm going to determine the output voltage at the center frequency. Remember, the center frequency represents the resonant frequency. So when this circuit is at resonance, the impedance of the inductor and the impedance of the capacitor are equal and opposite. They cancel. So the only resistance along this branch is RW. So if I set up a voltage divider to find Vout is going to be the voltage across this branch at resonance. My voltage divider would have RW divided by RW plus R times the input voltage. Remember, this is a band stop filter, so at the center frequency, this represents your minimum output voltage. The lowest voltage you will get out will be at resonance. So when we draw this response curve, I'm going to start with my XY axis. I'm going to label my frequencies. Same way as before, take the bandwidth, cut it in half, and do your critical frequency plus or minus that value. I'm going to show my maximum output voltage, 70% of that, and the minimum output voltage. Remember, the minimum occurs right at the center frequency. A few dotted lines for reference, and there's my curve. At the center frequency, I hit my minimum voltage. Once I reach the 2 critical frequencies on either side, I'm at 70% of the maximum. And the further away I get from that center frequency, the closer I get to the maximum voltage, which is what you put in, 100 millivolts. There's your frequency response for this band stop filter. So let's look at another band stop filter. This one is a parallel resonant band stop filter, where we're going to determine the center frequency, the bandwidth, the output voltage for an input of 12 volts, and the response curve. Notice that the inductor has a winding resistance of 8 ohms. Start with your center frequency. Use that to find XL. Use XL to find the quality factor. Use the quality factor to find the bandwidth. So those first 3 steps are what you need in order to find the bandwidth. Since this is a parallel resonant bandstop filter, I need to find the impedance at resonance using the formula for ZR. Remember, at resonance, L and C appear open, and the source is only going to see this value of impedance. And once I do that, this entire branch here has been replaced with ZR. If I were to set up a voltage divider to now find V out, that would have to be RL divided by RL plus ZR divided by, multiplied by 10 volts. So our output voltage is 1.18 volts here. And now we're going to draw the response curve. Here's my center frequency. Determine your 2 frequencies to the left and the right, also called upper and lower critical frequencies. We're going to label the maximum output, which was 10, because 10 is what goes in, so that's your maximum. 70.7% of your max. And your minimum. A few dotted lines for reference. There's my curve. So that's the frequency response for a bandstop filter. So we can very quickly and easily see what frequencies will not be allowed to pass. Anything within the pass band here, or stop band I should say, anything within the stop band here will not pass, and then anything outside of it will pass. So just as a recap, here are some of the new formulas that we discussed: bandwidth, and calculating the quality factor, calculating the resonant frequency. That's just a quick summary of some of the formulas we used today. So that wraps up our discussion on bandpass and bandstop filters. You can see that they are very useful when you have a certain set of frequencies that you want to prohibit from passing. As always, if you have any questions, please feel free to email me or send me a Canvas message. And that is the end of this video.